Are you being able to hear me, students? Good afternoon.
Good afternoon, sir.
Yes.
Here, sir.
So, yes. So let's start. Mm,
Yes, sir.
Yeah. Are you being able to see the screen? Hello.
Yes, yes, sir.
Yes. Is there a network problem? Are you being able to hear my voice clearly?
Yes, sir.
Okay. Okay. So we were looking at the first task scheduling problem, and in this problem we were looking at resource constraint scheduling. It is called resource constraint because the number and types of processors are given to us, no more, no less. So that is why it is resource constraint. It is given. Now, given this resource constraint, given the number and types of processors, we have to we have to schedule the tasks on the schedule the tasks in the task graph such that the total length of the schedule is minimized. So the total time required to execute all tasks in the application or controller is minimized. This is what the objective is. And we said that this is in this problem scenario, we have already done a hardware software partitioning. Therefore, we know which task execute on which type of processor. So this is known to us. So given this problem definition, we said that we will go we'll try to define a constraint satisfaction problem model for this, which can be taken as input by various software tools like LP-Solve, Cplex, etc. And then we can solve the problem the solver will solve the problem and give us the optimal solution. So the job, our job is to therefore formulate the problem as a constraint satisfaction problem. A constraint satisfaction problem is any constraint satisfaction problem is formulated by defining a set of decision variables and with and objective functions on the decision variables and associated constraints on those decision variables. So we need to define the object. First, we need to define what will be the decision variables. So what are decision variables? Those variables which give us a decision. The valuation of those variables is a decision in the solution. Assign task at this time step. This is a decision. Therefore, it is a decision variable. Or do not assign task this task at this time step. This is again a decision. So a combination of such decisions for all possible decisions give us a solution, and this is what a constraint satisfaction looks like. All these solutions may not be. So combination of all decisions on the decision variables give us a solution, but not all solutions are feasible solutions. And therefore, which are the physical solutions? Those that satisfy all the constraints that we design for this formulation. Those are feasible solutions. And one or a subset of these feasible solutions are the optimal solutions. You can have one optimum solution or multiple optimal solutions of the same cost. A subset of the feasible solutions become the optimal solutions. Right. And here our objective is to minimize time, length of the schedule, and therefore the schedule, therefore the decision variables for which the total time required to complete the execution of all tasks is minimized is your optimal solution. And among them, there will be multiple physical solutions which satisfy the constraints. Fine. So before that, I am in slide number 3. For this problem, we had defined n, a few variables, where n is the number of tasks. N is the number of tasks in the task graph. K, the number of processor types. Ti, the start time of Vi, and that is the decision, and will come after we solve the problem. TSI is the ASAP time of task VI. We understood what ASAP time is. TLI is the elapsed time. DI is the execution time of a task VI. That means the estimated execution time that this task will take, based on which we will design our schedule. And lambda is an upper bound on acceptable schedule latency. So with this, we said that the set of decision variables for our problem was what? XIL. We had a set of decision variables of the form XIL, where I, the index I denotes task and the index L denotes time step. So a certain variable, say x12, uh, gives the decision on whether task 1 will be will start its execution at time step 2 or not. So if x12 equals to 1, that means task 1 will start its execution at time step 2. If x12 equals to 0, then task 1 will not start at step 1, at time step 2. Okay, so this also we did. We generated what ASAP schedule is. Assuming infinite resources, what is the earliest time at which I can assign start times? That is the ASAP schedule. We also define what an elapsed schedule is. Given a value of lambda, we want to find out the latest time at which the task can be scheduled, considering again infinite resources available to us. That was the elapsed schedule. And we understood that our actual time will be somewhere between the ASAP schedule and the elapsed schedule. And we also looked at the first constraint. Then we came and saw we had started seeing the constraints on the decision variables. So we first said that each task has a unique start time. That was our first decision variable. And we said what? For time step L equals to the start time. So this was our first constraint. This is the first constraint. Are you seeing the box that I have drawn? Are you with me on slide number 8?
Yes, sir.
Yes. So this box represents the first constraint, and from there we can derive the time step at which a task is a time step. What this to the solution at what actual time a task will start is this the box on the right, but the actual constraint is the box on the left. What is that constraint? The constraint says that a particular task can only start at only one time step. So what are the possible time steps at which a task, the ith task can start? xil, L goes from TSI to TLI. These are all the possible times. So if TLI equals TSI is 2 and TLI is 6, say 2 and 6, then XIL will be XI2, XI3, XI4, XI5, XI6. These are the time steps. That means 2, 3, 4, 5, 6. These are the possible time steps at which the ith task can be scheduled. And among all these time steps, the task can actually start at only one time step, and hence summation L equals to TSI to TLI XIL must be equals to 1. And it has to be equal to 1 because it must start at one of these time steps. It cannot happen that it will not never be scheduled at any of these time steps. Then you cannot have a feasible solution at all. Okay. So this was it. So then we were looking at the example and seeing what were the constraints corresponding to this example. I think, is there any questions here? Then we move to the next constraint. Right? We understood this constraint. Any questions remaining? Because I am not physically being able to tell you on the board, I am allowing you this additional, you can ask again. if you want.
Got it, sir. It was clear.
Okay, fine, fine. So then we come to the next constraint, which is that dependency constraints in the task graph must be satisfied. And we said, what is a dependency? If you are with me in slide number 9, if you are not, you tell me. If you are with me on slide number 9, then you see that we have dependencies, directed edges. These directed edges represent dependencies. In my task graph, I have, suppose I have drawn this line between 10 and 11. So which means that there is a dependency between 10 and 11. So which means that 11 must start after 10 completes, possibly because the output of 10 will go to 11. Now, how do you represent that? So it first says that for all edges in the task graph. So the previous, just a minute, I'll go back once to the previous constraint and tell one last thing that I have left. So this constraint, the constraint that I have drawn on the left box, this constraint, you see, this constraint has to be satisfied by all tasks. So an additional thing that is missing while writing this constraint is for all I. This will be satisfied for all I. Do you get me? Because I, for all tasks, this constraint must be satisfied separately. It is not that it is satisfied for one task, it is done. When you're writing this constraint in your tool, software tool, you have to write for all I, this should be true. Okay. Okay. So now I'll go to the next constraint again. So now you tell me for what this dependency constraint has to be true for all edges in the task graph. There, the unique start time constraint had to be true for all tasks in the task graph. For the dependency constraints, it has to be true for all edges. For all. If you are with me at time step at slide number 9, you see that now I have given a for all symbol for Vji belongs to E. That means this constraint on this constraint that I have underlined has to be true for all edges. Vj, Vi belongs to the edge set of the graph. And Vj, Vi, if Vj, Vi is the edge, then that means you have a directed edge from Vj to Vi. Vj is the predecessor and Vi is the successor. If Vi is the successor, this dependency constraint must be able to say that Vi must start after Vj ends. So here you see on the LHS, if you remember the previous slide, this box that I have drawn on the LHS, this represents what? The start time for task Vi, right? Any confusion here? Tell me a yes, you understand this. L equals to TSI to TLI, L dot XIL. This represents TI, small ti.
Yes, sir.
Small ti equals to this. Acha. If you represent, if you understand this, that means you also understand that this box on the right, represents the start time of Vj, right? And
Yes, sir.
then this last part, Dj, represents the execution time of Vj, which means that if for any edge, this has to be satisfied. What? The start time of the predecessor plus execution time of the predecessor must be less than or equal to the start time of the successor. Are you with me?
Yes, sir.
Yes.
Yes, sir. So then I will go to the example. And so I will only look at the non-trivial dependency constraints because of just the number, those involving more than one possible start time for at least one task. For example, see, I have a constraint between task Let us understand this first constraint. If you understand the first constraint, all others will be easy. We said that the execution time of all these tasks in this task graph for our example is 1. This simplifying assumption we do. And we are considering this edge from 6 to 7. For this edge, what has to be? We have written the constraint for this edge 6 to 7. What have we written? We are seeing that, see what is see, I have L equals to TSI to TLI L dot XIL. Now, if this is the successor, so here our successor is 7. Now see L dot XIL. So what is TSI for for task 7? It can start earliest at time step 2 and latest at time step 3. So the TS7 is equal to 2 and TL7 equals to 3. If this is so, the value of L goes from 2 to 3, and the constraint on the left when broken down can be written as 2.x72 plus 3 into x73. Are you with me? Have you understood how 2 into x72 plus 3 into x73 actually represents the box on the constraint on the left of the greater than equal to sign?
Yes, sir.
Are you with me? Yes. If you have understood that, just see that what we have done. We have taken the RHS and brought it to the LHS in the example. Now, whatever it is, you see that what is happening for task number 6. Task number 6 can start in time step 1 and latest in time step 2. Earliest in time step 1 and latest in time step 2. So you have 1 into x61 plus 2 into x62. Now we are saying that so this constraint, just in a slightly different way, can be written as 2 into x72 plus 3 into x73 minus 6 x61 plus 2 x62 within brackets minus 1. What is this 1? Delay of or execution time of task number 6. So this one is execution time of task number 6, and that must be greater than equals to 0. Right?
Yes, sir.
Okay. Now you see that constraint, this cannot be considered separately. You have to consider this taking the unique start time constraint into consideration. Why? Because the unique start time constraint has told you that this x72 and x73 cannot be both equal to 1. Either x72 will be 1 or x73 will be 1, or either x72 will be 1 or x73 will be 1. Similarly, either x61 will be 1 or x62 will be 1. This has been guaranteed to us if constraint 1, that means unique start time constraint, has been satisfied. So now we can see that whatever is there in this bracket will be either be equal to 2 or will be equal to 1. It cannot be 3 because both of them cannot be 1 at the same time. Okay. And the first part with respect to task 7, that term, those two terms together, x2 into x72 plus 3 into x73, this term will either be equal to 2 or 3. Right? Are you with me?
Yes, sir.
Yes, sir.
Yes. Yes.
Sir,
If this is
please
so,
explain one more time this X7 to sir, my network. There is a network problem at my side.
right,
Now it is
right,
clear.
right. So what we are saying is that the unique start time constraint has told you that either x72 will be equal to 1 or x73 will be equal to 1. Both x72 and x73 cannot be together 1, right? This you are okay with,
Yes,
right?
sir.
Yes. So then 2 into x72 plus 3 into x73. these two terms together, the value of these two terms together will either be equal to 2 or will be equal to 3. It cannot be anything other than this.
Yes, sir.
Yes. And the value of the term within this bracket x61 plus x plus 2 into x62, the value of this term will be equal to what, 1 or 2, right?
Yes, sir. I got it, sir.
So then why this constraint is true, that is what I am understanding. Now I think you have understood.
Yes,
So
sir.
we proceed. Yes. So we proceed. Just a minute. So we have similar constraints for between x8 and x9. So the second constraint is for the edge x8 to x9. If this is self-explanatory, you should be able to understand what this constraint tries to say. It just tries to say that let us again, I'm going back to the edge 6 to 7. Edge 6 to 7, this constraint on this edge 6 to 7 is saying that if you start the 7th task at time step 2, you must start the 6th task at time step 1. Otherwise, my constraint will be violated. Because if x2 into x72 plus 3 into x73 equals to 2, then if x61 plus x plus 2 into x62 is not equal to 1, then my constraint will be violated. Are you with me? Because the value of the LHS will be equal to -1. If 2x72 plus 3x73 equals to 2 and x61 plus 2x62 that is also equals to 2, then the value of the LHS is going to become -1 and my constraint is going to be violated. So I cannot have the decision variables for which both x72 and x62 both are equal to 1. You cannot have that. X72 and x62 cannot be both 1.
Yes,
You
sir.
got me?
Yes, sir.
So if x7, this is saying because execution time equals to 1, it is saying that if x72 has to be equal to 1, then x62 must be equal to 1. X61 must be equal to 1. X62 cannot be equal to 1. If x73 equals to 1, then you can have you can have both x61 equals to 1 or x62 equals to 1. Any one of them can be equal to 1. Both cannot be 1 because the unique start time constraint has guaranteed that. So you have now understood what these dependency constraints are trying to say. Okay. These are the other constraints that we have. Any question, or then I will go to the next constraint. Any question? If you do not have any questions, then I'll go to the next constraint. Hello.
No questions, sir.
No questions. Fine. So next you have resource constraints. What does this resource constraints try to tell me? Try to constrain. How does it try to do that? It tries to provide a bound on the number of tasks that can execute on a resource of a certain type at a given time. So at a given time step, you have a total number of resources of a certain type that is given to me as input. Now the number of tasks executing on a number of tasks executing on processors of that type has to be less than equal to the total number of processors of that type available to me, right? Suppose I have 4 general purpose processors and 3 GPUs. Then I cannot have more than 4 tasks executing on the general purpose processor at any time. This has to be satisfied. This constraint has to be satisfied, that the total number of tasks which are to execute on general purpose processors at any given time step must be less than equals to 4. Similarly, you also have to separately satisfy that the total number of tasks executing on my GPUs has to be less than equals to 3 at any time step you consider, at all time steps. Are you with me? Yes?
Yes, sir.
Yes. So if this is so, then this constraint essentially tries to say, this constraint will therefore be for all what? For all L. That means the first constraint was for all tasks, the second constraint was for all edges, and the third constraint now is for all time steps. At all time steps, this resource constraint must be satisfied at all time steps. Now, if you go into the variable set that we defined as input, we saw that AK denotes what? AK is the number of processors of type K. AK was the number of processors of type K for the variable set, in the variable set that we defined, input parameter set. So the LHS must be saying something which tells that the total number of tasks that is executing at any time step L of type K must be less than equals to AK, right? Okay. Now, let us first understand this summation, because this is easier to understand. This constraint is a bit involved, but it is not very difficult to understand. What is I have drawn a box on the left summation. The left summation just gives you the summation over all tasks which are to be executed on processors of type K. So tau vi is a function that tells, tau vi is a function whose output gives me the type of processor on which vi has to be executed. Because I have done hardware software partitioning, I know this from my input. What is tau vi? Tau vi is just a function that tells me on which processor type should vi be executed, that is available to me. Now summation over what I'm doing, summation over all tasks of type K at any given time, right? And I am wrong, a bit wrong, in the sense that this is not only for all time steps, it is also for, oh, this is not only for all time steps, but it is also for what happened. It is also for K. So for all L and for all K, this has to be satisfied. At each time step, this constraint on the right has to be satisfied for all time steps, and at each time step for all types of processors. And then because we are given K and we are also given L, so this constraint can be designed for a fixed value of L and a fixed value of K. Have you seen? I have boxed out the constraint. Are you with me there? Hello.
Yes, sir. Hello,
Yes.
sir.
Yes. Tell me.
Sir, sir, it is a bit confusing. Could you please explain, the
I
core
will.
general purpose processor in numeral values and the time schedules?
I will explain the
I
entire constraint. Don't worry.
Sir, the first summation, sir, I have some doubt. I did not understand the first summation. Tau vi equal to k, that summation.
answer
Right.
AK is the type number of processors of type K.
Now, Yes, AK is the number. If go into if you have also opened the slides, you see I have a slide in which I have jotted down all my parameters, the symbols for all my parameters. There AK is the number of processors of type K, because I have assigned during hardware software partitioning, I know which task will go to which type of processor. Now I have multiple instances of that type of processors, right? So what I'm saying here is that tau vi equals to k, because I am writing this constraint for all L and for all K. The constraint becomes fixed for a certain value of L and a certain value of K. So I know what is the value of K, what is the type of processor for which I am trying to satisfy this constraint, and what is the value of time at which I'm trying to satisfy this constraint. This is known to me. So K and L is fixed inside the constraint. This must be satisfied for all L and for all K. Now let us get inside the constraint. The first summation inside the constraint is doing what? It is summing over all the values, all the tasks. It is summing over all tasks which are to be executed on processors of type K. Like for example, we said that suppose you have 10 tasks and 6 among which will execute on general purpose processor. So for 6 of these tasks, tau vi will be equal to K, where if K denotes general purpose processor, if K denotes general purpose processor, then tau vi, this summation will be equals to 6, because for 6 tasks means you will have 6 different values. Not the summation will not be equals to 6. What you will have is that for 6 different tasks you will satisfy tau vi equals to K. For all such, you will get inside the second summation. I will now try to explain the second summation, and then the entire the LHS, and then I will get into the example, and then you will understand the entire thing. But first try to understand now the second summation, even if you have not understood the first summation. So what is the second summation trying to tell me? This is very important to understand. See what is written here. A task Pi is executing at time step L when m equals to L minus di plus 1 to L xim equals to 1. So consider any time step L, any time step, say 10th time step. And let us say that my execution time for that task, for a task is 3. I'm trying to understand whether this task whose execution time is 3, is it executing at time step number 10? Right? Suppose this is the question I have asked. Again, understand the question I have asked. I have a task whose execution time is 3, and I want to know whether this task is executing at time step number 10. Now, when will this task whose execution time be 3 be executing at time step number 10? If this task has started in time step number 7, then 7, 8, 9, it has executed at the 10th time step. This task is not executing. However, if the task has started at time step number 8, then it will complete at time step number 10. So it is executing at time step number 10. If the task has started in time step number 9, then it is executing at time step number 10. If the task has started in time step number 10, then it is executing at time step number 10. So a task whose execution time is 3 is executing at time step number 10 if it has either started in time step number 8 or 9 or 10. Are you with me on this? Don't see the constraint. Understand what I have just told.
Sir, what is that
Yes.
3?
3 is the execution time di of task ti.
So, sir, between these 3, we can take any time step under between it under
No.
10.
Again. I'm saying I am checking at time step number 10. What am I checking at time step number 10? Is task Ti executing at time step number 10? This is what I want to check. Now, how am I checking?
Executing means start or end.
Executing means continuing to execute. It can start or it can end, but it is executing.
Okay.
It can be in the middle of execution also. Suppose execution time is 5.
Yes,
The
sir.
execution time, the total DI value is 5. So then it will start at some time step, it will continue executing for some time step and will end at a certain time step. At all these time steps it is executing, right?
So sir,
Right.
means if it is start time is 4 and its end time is 6, so if we check on 5, so it will be executing on that time.
Yes. Now let us understand this box once. Then again, if you have a confusion, I will come back. This box. Okay. So for us, this L is equals to 10. This L over the summation, or the M equals to L minus Di plus 1. Let us understand what M equals to L minus Di plus 1 telling me. So now see, L was 10, Di was 3 plus 1. So 10 minus 3 plus 1, 8. So M is equals to 8 and L is equals to 10. So I am checking from what? From M equals to 8 to M equals to 10. And what am I doing? Summation xim equals to 1. If summation xim equals to 1, that means if summation xim equals to 1, what does it mean? This task has either started in time step number 8 or time step number 9 or time step number 10. For all these three cases, if any one of these three cases is true, then it is executing. Because of the unique start time constraint, xim cannot be equals to 1 in more than one value of m for more than one value of time. So if xim equals to 1, it means that either Ti has started in time step number 8 or 9 or 10. Are you with me?
Yes, sir. Yes, sir.
Yes, sir.
Yes. So then you have understood a very important part of this constraint. That summation m equals to L minus Di plus 1 to L, xim equals to 1. If xil equals to 1, if task Ti has started and if task Ti is executing at the current time step. So this part will be equal to 1. M equals to L minus Di plus 1 to L xim will be equals to 1 if this task Ti is executing at the time step, at the current time step L. If this is so, then see, this is what the inner summation is in the LHS of the constraint. In the LHS of the constraint, this is the inner summation. Right?
Yes,
Yes,
sir.
sir.
Right. So now,
Sir,
right, tell me.
sir, are you proceeding or
I am proceeding. I
sir?
am proceeding what? Ask, then ask.
Sir, sir, it is m is equals to 8 and L is equals to 10 in the right side summation.
Hmm. M equals to 8 and L equals to 10. Yes.
Yes, sir. So, sir, what 8 and 10 means what is start and
8
end
and 10.
means?
No, not start and end. Not
Yes,
start and end.
yes, sir.
I am saying, what am I trying to check? I am checking, mark my words. I am
Okay.
checking whether this task Ti is executing time step number 10. And then I am saying that this task Ti is executing at time step number 10 only if it has started in time step number 8 or time step number 9 or time step number 10. How
Okay,
do
sir,
you
I
know
got.
when a task starts? If the corresponding xim variable equals to 1, for
Yes, sir.
xi8 equals to 1 or xi9 equals to 1
And
or
or
xi10
exciting.
equals to 1.
So,
Then
sir,
this
M
summation
is
will,
the hello.
M is the
M is the start, but L is not the end. It is some
yes,
main
L is
time
not the
step which we are
M is
checking.
the start.
Sorry.
Correct. M is
Okay,
the
right.
start, but N is not the end. Yes.
Thank you.
So now you have understood the second summation on the LHS. Now, in the second summation of the LHS, it can be true for any task. But which tasks are valid? That is being given by the first summation. Which tasks are valid? Those tasks that will execute on the kth type of processor. Only for those tasks, I will consider those i's. So in XIM or DI, in the inner summation, you are using a DI and you are using an XIM, where I denotes the task. Which task can be considered in the inner summation? Only those tasks, not summation over all tasks. Only those tasks which are to execute on my current type of processor. Are you with me?
Yes, sir.
Are you with me? Yes. Yes. If this is so, now you should be able to understand what this first summation means. The first summation extracts out those tasks, those i's, which are executing on the kth type of processor. So you are summing up overall tasks which are executing on the kth type of processor. So sum overall tasks for which tau vi equals to k. This is what the first summation tells me. Okay. Any
Yeah, yes,
confusion?
sir.
Yes.
No, sir, no
So
control.
no. So then what is this constraint telling me? This constraint is now telling me that the total number of tasks of which can execute on processors of type K, the total number of such tasks which can be executing at time step number L must be less than or equal to AK. Are you with me? AK is the total number of processors of type K, and the LHS is saying what is the total number of tasks that can be executing on processors of type K at a given time step L, that is executing, and this number has to be less than equal to AK. Give me a yes if you have understood this. Then we will understand this
Yes.
through the example.
Yes, sir.
Yes, sir.
Yes. So, assuming that you have, in this example you have two types of processors, like one is the plus type, the other is the start type. Suppose that you have two plus type processor and two start type processor. Okay. If you have this, then resource constraints on start type processors. So what will it be? At time step 1, so we are doing this for all time steps and for each time step and for each type of processor, for all L and for all K. So I told that inside the constraint you have the L and K fixed. So hence we are seeing the constraint for the start type of processor at time step 1. What is it saying? If you have two types of processors, then possibly how many tasks can be executing at time step 1 of start type x11, x21, x61, x81, because all these can possibly be scheduled in time step 1. But how but this number actually has to be less than or equal to 2. This is what my constraint tells me. The first constraint told me that each of my tasks can execute only at one time step, cannot execute at a unique time step, cannot execute in multiple time steps. The second constraint told me that the dependency constraints must be satisfied. The third constraint is telling me that at each time step, for each type of processor, the total number of tasks that can possibly be executing at that time step on that type of processor must be less than or equal to the number of processors of that type that is available. That is why it is saying that x11 plus x21 plus x61 plus x81. Why is this 1? Because this 1 the later one. So x1 1, that means task 1 at time step 1, task 2 at time step 1. At time step 1 you have 4 possible tasks which can execute on start type processor, and that has to be limited by 2, at most 2. Have you understood? Have you understood this point? Have you understood
Yes.
the first
Yes, sir.
constraint? Yes.
So, sir,
So these
it
are the
means, hello,
yes, tell.
sir, I got this that it means that either X11 or X21 can be started simultaneously, or X11 or 61 or X11 8, or any of the two tasks can be.
Any one, any two,
Yes,
less than or equal to. So none at all can is also okay. So 0
yes,
or
yes, sir.
1 or 2,
Yes, yes,
at
sir.
most 2. Similarly, for the second time step, at for the start type processor, x32 plus x62 plus x72 plus x plus 8x2 has to be less than equal to 2, because at the second time step, who can possibly be scheduling, who can possibly be executing either 2 or x62, because 6 can execute in 1 or 2. So 6 can be executing in 2. You cannot, means provided my dependency constraints and my unique start time constraints satisfy, then x1 x6 sorry x61 or x62, anyone could be true. So x62 could be true. So but the constraint says that x32 plus x62 plus x72 plus x82 has to be less than or equal to 2. Are you with me? Okay. For time step 3, you have x73 plus x83. See that the on start type processors, only 2 tasks can execute at the third time step, x73 plus x83, because of the other limitations, ASAP, ALAP, dependency, the unique start time, all these things that we have already studied. Based on that, at time step 3 you see that either x73 or x83 can be there, and this is the constraint that must be satisfied. If you are not understanding, ask. So this is what we had to do for time step 4. There are nothing to execute for the start type processor. There is no constraint for the start type processor, because no tasks will be executing. For the plus type processors, what is happening at time step 1, only x101 can be equals to 1. So the constraint will be x101 less than equals to 2. For time step 2, what can be x92 can be equal to 1, x102 could be equal to 1, x112 could be equal to 1. You understand that x102 and x112 can never be equal to 1 together because of the dependency constraint. But we do not bother here. That will be taken care by the dependency constraint. So here just we are writing that x92 plus x102 plus x112, whoever are one within this, maximum you can have is two of these three can be one. Not more than 2 can be equal to 1. x92 plus x102 plus x112, among them only 2 can be equal to 1 at most. This is what it is just telling me. Similarly, at time step 3, what do you have? x43 plus x93 plus x103 plus x113 less than equals to 2. And for time step 4, x54 plus x94 plus x114 less than equals to 2. If you have understood this, then I will proceed to the objective function. Have you understood this constraint?
Yes, sir.
Yes. So now I will proceed to the objective function. So now what is my objective? See the entire CSP model. What does it tell me? Sorry. What does it tell me? Minimize TN. Sorry. So minimize TN is my objective. Why is this a correct objective? Can you tell me what is TN? What is TN? What is TI? What is TI?
Start time of execution of task I.
Start of execution of task I. So Tn is the start of execution of task n, which is the last sync node. If you go to the previous, this last node is numbered n. So among all feasible solutions, what are you trying to minimize? The start time of the nth node. And I know that all tasks will finally come and converge at n. So if I minimize the time at which the nth node starts, that means I have achieved my objective, which is to minimize the total length of the schedule. Total tasks by which all tasks, total means the time by which all tasks must complete execution. This is minimized given the restriction on resources. Are you okay with the objective? Have you understood the objective?
Yes, sir.
Yes, sir.
Yes.
Okay. So then the entire formulation becomes this. Minimize Tn such that constraint 1, constraint 2, minimize Tn such that constraint 1, constraint 2, and constraint 3 are all satisfied, and given that all xi's are binary variables. So the first one is unique start time. Second one is dependency. And the third one is resource. Okay. Are you, if you have understood this, I'll quickly go back to slide number 10. If you have understood the entire, this is the entire formulation. This formulation can be directly taken as input by LPsolve or any other industry-rated tool like IBM Cflex, and it can solve your, give you an optimal solution if you give this formulation to it. Have you understood? Then I'll go back to the previous slide. Give me a yes.
Yes, sir.
Yes. Now I'm saying that what this is a, you have a heterogeneous number, different types of processors here. But suppose you are given a simple multi-core system in a CPU with say 8 cores, all of the same type, and you are told that this is the embedded system you have, only software but 8 cores, and you are given a task graph. Schedule my task on the task graph, schedule my tasks in the task graph on these 8 cores, all of the same type, such that my total time is minimized. Then this problem is called the homogeneous multiprocessor scheduling problem, a very well-known scheduling problem, such that the total schedule length, which is also called make span of the task graph, is minimized. Make span of the schedule is minimized. Make span means the length of the schedule. What do you mean by length of the schedule? The total time within which all tasks are executed. Alternative names for that. So this is the homogeneous multiprocessor scheduling problem. Now, the homogeneous multiprocessor scheduling problem can easily be derived from what we have written is this. There, K is just one type of processor. So for that, what will happen, if you modify the resource constraint a bit, AK will then represent the total number of homogeneous processors you have. That means 8. You have 8 core you have an 8 core CPU. 8 core CPU, all cores are of the same type, general purpose processor. This 8 core CPU, then AK will become 8, and then this K will only have one value. So for all K will not be there because K is now known, and this summation is no more required. This summation is required, but what will happen is that for this will happen for all I, for I equals to 1 to n for all tasks, and this AK will be equal to the total number of homogeneous cores that you have. Total number of processors. So what have I just done? I have just tried to tell you, if you are given a homogeneous multiprocessor scheduling problem, then how easily you can just simplify whatever you have just studied and say that this is my formulation. Given a set of homogeneous multiple processors, I will be able to schedule a task graph such that schedule length is minimized. Are you with me? Yes, no?
Yes, sir.
Yes. So then with this, we come to the end of this class. Happy Puja holidays and meet you after the pujas. I will meet with you on next Thursday. So 1 week gap. Wednesday you have an exam of madam. Yeah.
Yes, sir.
Thank you, sir.
Yes. Thank you. Happy Puja.
Thank you, sir.
Happy Puja, sir.
Yes, sir.